This is just a real integral representation of Bessel function. It's in particular J. There are other for other Bessel function, other integral representation. And now this is a new, another new derivation. This is similar to what we did in the homework, chapter 11 homework. Because if you remember that homework actually used this integral representation to identify the Bessel function, identify the coefficient as Bessel function. So again, to go back to the generating function. Okay. Now the idea if we consider this this generating and generating function and do a contour integral and about the origin, because we are taking the expansion in T, and then that's involved in inverse order of T also, but inverse order of T is singular at T equals 0. We can just consider a contour. So whatever contour that circle the origin, like a circle or something like that. And consider C. And in particular, we can actually set the radius to 1, a unit circle. Right? And what we want to do is just consider this loop integral over C, this contour C of this generating function, and then divided by T to the N1. Yeah. Right, and now we can substitute this one to represent the exponential function. That is this directly substitution. There is 1 over Tn plus 1 sum over. Now you can use n. You can use like m. Base of m. M. Right. And then dt. And you can also combine that this power to this one, so you can basically change that, cancel this one to this becomes m minus n minus 1. And then what is this? You remember what is this? The complexity, still remember the complex. So most of the m will be 0. Which m will give you non-zero? Because I mean, you forget about it. You can say that T is this along this lines. T is the unit circle is e to the I theta, right? Right. So the dt becomes I e I theta d theta, right? And so we can change the loop integration to take the summation out to d theta, and theta is from 0 to 2 pi, right? Just going around, and you have the I. But this one, the dt is your I d theta. I e to the I theta. And for J sub n, just keep it. There's nothing you can do about this. Because, I mean, this doesn't involve t anyway, so all the t is here, so it's e to the I m minus n minus 1 theta. Right? And you can cancel this e to the I theta with this minus 1, so you can cancel this with this minus 1. So what is this now? Is it easier to see? This mx. And the rest is this integration. And what is this integration? Which one is non-zero? Which m will give you non-zero? Yeah, when m equal to n is when m equal to n, the exponential is 1, right? 1, and then d theta will give you 2 pi, right? And then you are Fi, right? But when m is not equals to n, this is an integer, right? And e to the I, an integer times theta, is the sinusoidal function. You integrate to 2 pi, that would be 0, right? So, right, so that, so you have 2 pi I delta mn. That is given by 2 pi I j sub n. Right, so all this just derivation, so you show that j sub n is equals to this. So this, write it in here. This is 2 pi I j sub n x. So you can say that j sub n x is given by this integral divided by 2 pi I. It's okay. So that's the basic form, but then you can do it a little bit differently, because you can now these are just derivation. I copy it over here, so now I can erase that. And then again, using this to change it to a theta integration, right? The 2 pi ij sub n equals to this one equals to, the theta integration. Again, you have I e to the I theta d theta for dt. Now the t to the n plus 1 in the denominator becomes exponential minus n plus 1 I pi I theta, right? Yeah, that's this one. And then exponential function is over 2. And this 2 is, the first one is e to the I theta, and minus 1 over e to the minus theta, e to the minus I theta. Right? And that's basically it. And now again, you can do the cancellation, e to the I theta. This one cancels with the 1, right? And so, or if you want to write it, combine this exponential factor to here, and right now, so you can have I, you can cancel with this I. So the nx is now becomes 1 over 2 pi, integrating d theta 0 to 2 pi, and exponential function x. Now you can simplify that e to the 5 theta minus e to the I theta, use the Euler relation. So this is 2I sine theta, right? So 2I becomes I x sine theta. And this one, you move it to the exponential function, becomes minus I n theta. Right? So that is another way you can write it. This should be equation 14.17. right? X sine theta minus n theta d theta, right? Yeah, except that that equation still keep the I, but you can, but I can cancel, so this is the right way, right? And I mean, if you want, you can divide 14.18 out, because this is you have the symmetry of this function, right? Because the argument is odd function in theta, right? And odd function means you can actually first the because this is periodic function, you can actually change it to minus or minus theta to theta instead of 0 to 2 pi, so minus pi to pi. Now for if the integram is odd function, it will give you 0. So you only keep the integram, the even function part of the integram. The argument is odd. To get an even function, you have an even function of an odd argument will give you even function. If you have odd function of an odd argument will give you an even function, right? No, the odd argument of this argument will give you the odd function. So that will cancel. So you want to keep the exponential, the even function part of the exponential function, which is cosine, right? So to simplify that, and then you can, that will give you the twice of the integral from 0 to pi, right? So 2 of 0 to pi, so you want 1 over pi 0. So I have how much time? 3 minutes. 0 to pi and d theta, and just write the cosine part. Sine theta. Right, so the integral becomes a real integral instead of keeping the exponential I function. Right, and that is 14.18. Is okay? So that you can express the Bessel function this way, and again, this is for integer order, for n, for integer n, right? For integer n, you have this one, and then the rest is some special case like n equals 0, or that doesn't matter that much. I think that's almost all. The next section is really simple. It's just talk about the 0 of the Bessel function and list a table of 0. And all these Bessel functions are oscillatory. So this should be a graph somewhere. Yeah, the figure 14.1, you can see that all these functions are oscillatory. So, and then by the series solution, you know that the J0, only J0 have non-zero value at x equals 0. Actually, it's defined as 1. By the series solution is 1. So it's oscillatory. But the oscillating, the period of oscillation is varying. It's not the same. So this 0 of Bessel function is not regular. You need to look up the table or calculate it numerically, except that for large argument, which we'll cover later. So for the asymptotic relationship, asymptotic expression for the Bessel function, the period become more or less more regular. But at least for the first few, it's not that regular. And the amplitude is decreasing. So that's J. And then all the other J's start from 0. And then the kind of, I mean, again, based on this recurrence formula, you can see that the 0 will go through. So this is the first 0 of J sub 1 will go through between these two 0, and likewise for the other 0. And there's some property, and then J sub 2, we start with x squared because of the power series of the small x argument or for small x dependency of J sub 2 x squared, proportion x squared. So it actually goes through all the way between this one, actually circle. There's now this numerical, right? It's like that. There's two, but they are all oscillatory. The zeros, that the first few zeros are not obvious, so you need to look up this table. And the zeros are important in some way, and the textbook has two simple example to to express to illustrate the use, how you use the zero. The first one is diffraction. The second one is this normal mode in a resonant cavity. Both of them will be covered in E and M. So I don't know whether we will go through that in details, but those are, these two examples are quite straightforward, quite simple. But you probably go through the more difficult one in next Monday, the contour integral representation. Okay, I think I'm out of time. Any question up to here?